but it's critical to understanding the early universe. Scientists think it took less than a millionth of a millionth of a millionth of a millionth of a second for the universe to expand from the size of an atom to a baseball. That may not sound like much, but it's like a golf ball expanding to the size of the Earth in the same amount of time. That means it was expanding faster than the speed of light. That's fast.
So many things were happening so fast in the early universe because everything was so close together that we need a new unit of time to describe things.
It's called Planck time. To understand just how short a Planck time is, consider this. There are more units of Planck time in 1 second than all the seconds since the Big Bang. The math is mind-blowing. There are more than 31 million seconds in a year, and it's been 14 billion years since the Big Bang. So multiply 31,556,926 by 14 billion, and what you get is a really big number.
It's a time scale that's so small that all human intuition goes out the window. If we look at our watches and measure 1 second, we can ask how many Planck times is that? Well, it is a billion, 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 billion Planck times.
So, now the Big Bang is only a few Planck times old. An exploding mass of pure energy, expanding faster than the speed of light. In the next few Planck times, the universe as we know it will be born. A fraction of a second after the Big Bang, the universe is so small it can fit in the palm of your hand. But in another tiny fraction of a second, it expands to the size of the Earth. Then, moving faster than the speed of light, it grows larger than our solar system, and it's still just a raging storm of superheated energy.
It'd be hotter and denser and more violent than anything that we can experience in the universe today. Even the interior of a star is calm and serene by comparison to the violence of the earliest moments of the Big Bang.
Temperatures were so hot that even the atoms of your body would disintegrate. So hot, in fact, that the atoms would be ripped apart.
How hot? Trillions of degrees hot. But as the universe continues to expand, it also begins to cool. Dropping temperatures trigger the next stage in the universe's evolution. The raw energy of the explosion transforms into tiny subatomic particles. It's the first matter in the universe. This conversion of energy into matter was predicted by Albert Einstein years before anyone started talking about the Big Bang. It's the one scientific equation every school kid knows.
There is one very familiar formula, and that is E equals mc squared. It says something about the creation of the universe. It says even if the universe is created just out of pure energy, that because energy can be converted to matter and matter to energy, that you can get all of the stuff that we see in the universe from this pure energetic event.
Einstein's little equation had a big impact. It led to the first nuclear bombs. In a nuclear explosion, a small amount of matter is converted into an enormous amount of energy. As the universe was forming, the exact opposite happened. Pure energy transformed into particles of matter.
You don't need to create matter in the beginning, you just need energy. And energy alone can lead to the creation of an entire universe.
In just a fraction of a second after the Big Bang, the building blocks of our universe begin to take shape. But this first matter is like nothing we see today.
The stuff of matter has been very different over the age of the universe. What we now think is normal matter was not at all normal in the earliest moments of the Big Bang.
That's because conditions were so extreme. There were no atoms yet. But there were tiny subatomic particles.
In the earliest moments of the Big Bang, the universe was so hot and dense, there were great amounts of energy. And so particles were being created all the time, and energy and matter were transferring back and forth in this hot, dense soup.
That earliest matter was too unstable to start forming the universe as we know it. Think of it like this. Imagine rush hour at Grand Central in New York City as that superheated early universe. The commuters racing through the main concourse are subatomic particles.
If you look at a crowd of people, a large crowd of people, they may appear random. That random quirky motion is very similar than what was happening to the particles in the universe in the earliest moments of the Big Bang.
The extreme temperature of the early universe energizes the subatomic particles. They appear, they disappear. They race around at incredible speeds. It's pure chaos.
It's like people. If they're excited and running around fast to catch trains at a train station, they'll be moving around quickly. But eventually they calm down and get slower. That's what's been happening to our universe in a sense. The particles are moving around very fast, and as the universe cools down, the particles move more slowly and in some sense less randomly.
As the universe cools, the particles stop changing back into energy. Now, there are more and more subatomic particles, but it's still a hot, violent place. All this is happening in fractions of a second, too small to detect. But the Big Bang is moving into a critical stage now. A titanic battle between matter and the one thing that can destroy the universe before it even gets started: antimatter. Everything in the universe is made from matter. From the smallest rock to the largest star. And all the matter there will ever be was created from the pure energy of the Big Bang. Einstein's equation, E equals mc squared, says that energy transforms into matter. But it was just a theory. Today, science is able to test that theory. This is CERN in Switzerland, home to the world's largest machine. It's the size of a city and engineered to recreate the conditions millionths of a second after the Big Bang.
If we want to probe ever smaller scales, paradoxically, we need an ever bigger machine. There's just no other way of doing it. So big machines means small physics, means early times, and therefore getting closer and closer to the origin of the universe itself.
This monster machine is called a collider. It's designed to take us back to those first fractions of a second after the Big Bang. It's a 12-foot wide, concrete-lined circular tunnel, 17 miles around. The collider makes tiny particles of matter smash into each other at almost the speed of light. For a split second, those collisions generate turbocharged energy similar to the explosive force of the Big Bang. And then, that pure energy briefly transforms into matter just like it did nearly 14 billion years ago. But a monster machine needs a monster detector to see these collisions.
This detector is 5 stories tall and weighs over 7,000 tons. And 7,000 tons, to give you a sense of perspective, is the weight of the Eiffel Tower.
But as big as it is, it can't see the actual particles of new matter. They hang around for just a split second and move so fast, it can only record their trails.
There's a lot of energy in these particles. They move very, very quickly, and so you need a very large amount of detector in order to be able to map the path of these particles very precisely. So the detector is so big because you need better resolution. It works exactly the same as a camera. The more pixels you have, the better the picture. It's exactly the same here. We just have a 5-story camera.
Scientists hope that it'll reveal just how energy transforms into matter. But not just any matter. The kind of matter that emerged 14 billion years ago, at the dawn of time itself. But the dawn of time was a critical moment in the birth of the universe, because pure energy also produced one of the most dangerous things in the universe, antimatter. That's right, antimatter. It's real.
Antimatter is the mirror image of ordinary matter. However, matter has one charge, and antimatter has the opposite charge. If there was an anti-me made out of antimatter, that person in principle could look exactly like me. Same personality quirks, same everything, except of course when I decide to shake his hand. At that point, we both would blow ourselves to smithereens in a gigantic nuclear explosion.
Matter, with a positive charge, locks horns with its arch enemy, antimatter, with a negative charge. The fate of the universe hangs in the balance of this epic battle. Equal amounts of matter and antimatter will cancel each other out. Not good.
A universe with equal amounts of matter and antimatter is equivalent to a universe with no matter at all, because the matter and antimatter will annihilate back into pure radiation. And there'll be nothing interesting, no stars and galaxies and people in between.
Like a cosmic game of Risk, the side with the most soldiers wins. The score was very close, but there was a winner.
For every billion particles of antimatter, there were 1,000,000,001 particles of matter. That was the moment of creation. The one extra particle of matter in each little volume survives enough to form all the matter we see in the stars and galaxies today.
One in a billion might not sound like much, but it's enough to build a universe.
We're the leftovers. So believe it or not, everything you see around you, the atoms of your body, the atoms of the stars, are nothing but leftovers. Leftovers from this ancient collision between matter and antimatter.
Lucky for us, there was enough left over to make all the stars and planets. And the universe is still less than 1 second old. But now, it's swarming with tiny, primitive particles. The next stage is assembling those tiny particles into the first atoms.